Ladies and gentlemen, welcome to the Quantum Championship. In the red corner, weighing almost nothing and chilled to near absolute zero, and backed by Google and IBM, we have the Superconducting Qubits. And in the blue corner, levitating in air and controlled by lasers, the trapped ion qubits. But wait, that's not all. In the shadows, we got photon qubits zooming through chips, spin qubits chilling inside silicon, and even diamonds with atomic holes flexing their quantum powers. But hold up, why are there so many types of qubits in the first place? A regular bit is literally just a transistor. It's on or off. That's it. Done. So why does quantum computing feel like this chaotic battle royale? Well, let's break it down. Alright, but why is this even a problem? Well, here's the deal. Classical computers are pretty straightforward. You got these tiny switches called transistors. You got billions of them flipping between 0 and 1 using voltage. This is also called a bit. See, there's no magic, it's just solid engineering. But a qubit? Nah, that's a whole other beast. A qubit can be 0, 1, or it can be both at the same time thanks to this quantum voodoo magic called superposition. It's powerful, but it's super fragile. You can't just build a qubit with regular tech. You need a physical system that naturally follows quantum rules, such as superposition, entanglement, and much more. And those systems can be super annoying. They hate heat, hate noise, hate being looked at. You basically gotta pamper them in a vacuum while playing some lo-fi beats to help keep them calm. So researchers got creative and started asking some questions like, what if we levitate atoms with lasers? What if we freeze circuits to space chilling temperatures? And what if we use light itself? Boom. Now we've got different physical flavors of qubits, all with the same goal, but with totally different science. Okay, so how do you then actually build a qubit? Well, this is where it gets messy. See, unlike classical bits where transistors run the game, in quantum land, it's like picking a fighter in Super Smash Bros. They all have different strengths, different weaknesses, and different vibes. So let's go ahead and meet the roster. First up, we have the superconducting qubits, aka the speedster tank. These guys are basically loops of superconducting metal that only work when you cool them down to nearly absolute zero. Once you get that current flowing, a quantum state forms, and boom, you've got yourself a qubit. This is the method used by big names like Google, IBM, and Rigetti. The main advantage, they're lightning fast, like nanoseconds fast, making them ideal for speedy quantum operations. But here's the catch. They require these massive million-dollar dilution fridges to keep everything cold and stable. And even then, their quantum states don't last long. So while they're powerful, they're also super expensive and pretty high maintenance. Next up, we got the trapped ion qubits, or the laser sniper. Imagine suspending single atoms in mid-air using electric fields, then precisely hitting them with lasers to control their quantum states. It sounds like sci-fi, but it's definitely real, and companies like IonQ and Quantinuum are making it happen. These qubits are incredibly stable, with some of the longest coherence times out there. But on the flip side, they're slower than their superconducting cousins, and scaling up is quite tricky. Each individual ion needs a dedicated laser system, which adds complexity and makes large-scale systems harder to build. Alright, let's move on to the photonic qubits, or the light speed runner. Photonic qubits are made out of, you guessed it, light. They use photons traveling through optical circuits, which means no cryogenic cooling is needed. These things move at the speed of light and are awesome for sending quantum information over long distances, like in future quantum internet setups. But there's a big challenge. Photons don't naturally interact with each other, which makes building gates and doing computation super difficult. For these qubits, error correction is a big nightmare. Still, companies like Xanadu and PsiQuantum are all in on this approach because the scalability potential is huge, if they can crack the code. Next up, we have the spin qubits, aka the silicon underdog. This type of qubit uses the spin of electrons trapped inside silicon, basically using the same material we already use in regular computer chips. The idea is that if we can get this to work reliably, we might be able to manufacture quantum processors in the same fabs we use for classical ones. Spin qubits are tiny and theoretically super scalable, which makes them really promising. That said, the technology is still pretty fresh and not as well developed as some of the other methods. Intel's been pouring a lot of resources in making this work, hoping it becomes the go-to qubit type down the road. Finally, the last qubit in our roster are the nitrogen vacancy centers, or the Diamond Ninja. These are quantum systems formed from defects inside of diamonds. You knock out a carbon atom and swap in a nitrogen atom, and you end up with a super stable quantum state. Now, one of the coolest things is that NV centers can operate at room temperature, and they're insanely good for sensing stuff like magnetic fields and tiny changes in the environment. Now, while they're not really leading the charge when it comes to quantum computing, they're absolutely crushing it in quantum sensing and metrology. So they might not be in the main battle, but they're definitely winning some important side quests. So yeah, turns out qubits aren't just souped up bits. They're physics playgrounds, and every type comes with its own chaos. But one day, someone's gonna figure it out, and that could honestly be you or me. And when they do, that qubit type will unlock breakthroughs in chemistry, AI, security, and who knows what else. Until then, the quantum championship rages on. Now, if this video helped you finally understand the different types of qubits being researched on, drop a like and let me know in the comments, which qubit are you placing your bets on?